Jennifer told me to write down. Apparently you can do screen recording, so that's what you are watching right now. And I'm enabled commentary, so I don't know. You can record this, I guess. But I was explaining to Jennifer what I guess you'd call the usefulness of calculus. Which I'm a big fan of. I'm sure you all know that. Or some of you might know that. Whoever sees this video. I talk about it a lot, so like, let's say you have, like, a mountain. Very big mountain. Maybe like Mount Everest. And let's say you just made it to the top. Yay. I don't know what this flag would be. Okay, you made it to the top. It was probably cold up there, so maybe a little hat. Okay, I realize I'm like drawing like a witch. Maybe like now it looks like a bandit. Okay, just a really bundled up guy. Yeah, that looks good, I suppose. And let's say you're celebrating up there, but you accidentally kick a snowball off of the mountain. And as some of you might know, there's a little base camp right here. Oh, it's probably a tent, isn't it? They probably would have fires up there, so. Alright, here's base camp. I think they've got, like, little flags. Really enjoying this, just drawing. It's very fun. They got, like, little rock cans. Those things are cool. Because you can see them, even if there's, like, a snowstorm or something. Alright, so let's say, and you want to know, this thing's probably going to get bigger as it goes down, you know, and you're wondering if you should phone in and warn them or something. I don't know, whatever you might do. Maybe nothing, but you know that snowball's going to get bigger as it goes down, and by the time it gets to here, it's going to be colossal, because you're probably like a good, like, 5,000 feet. This is base camp. This is probably like 10,000 feet below you, at least. So obviously this thing's going to get super big. So you're wondering this in your head. And you're wondering if you should or shouldn't. Your brain's kind of doing all this math and is like, you know, how big is it going to get? Should I tell them? Will it be fine? I don't know. But let's assume the worst case, because I don't know. Why not? That's what calculus is. I guess it's assuming 0 to infinity, 0 to 100. So without that nice drawing, let's just kind of simplify it a little bit. So you've got this snowball, and it's going to be probably like this big at the end, because it's going like down like, I don't know, what did we say, 10,000 feet? So obviously you're looking for like the final size at a final time. Of this guy right here, the snowball. And all you know is that time's going to go by. But we can make a pretty good inference about how the snowball is going to change, just because, you know, it might not start out big, but it slowly, like, accumulates, like, more snow. I know they're kind of like ovals, but that's really, those are some tight spacings. But you want to know how this changes as time goes on, because you're trying to get the final size at a final time. So we could say that the change in size, let's say, just because we want to know the change in size, really, because it's starting out very small, we want to see if it's going to get big or not. And we want to see, what that's going to be. And, from high school chemistry or something, the delta symbol is representative just a change, like delta T, change in temperature, for example. So like your change in size, let's just say change in S, change in time, T. So your del S, del T. So we know that we can't really make it, we know that this, for example, is 10,000 feet down elevation. We know it takes some amount of time for that to fall. So we can get, a good estimation. Or we could even say, let's just change it to feet, just because then it could be, more broadly applicable. Just because we would have to solve to get, how long it takes to go 10,000 feet. And then you'd have to express things in terms of feet. But anyways, that was just a bad side note. But instead of time, let's say, I guess let's say time, just because at each instance it's a different size. So hence del S dt. And so how does the size of the snowball change with respect to an amount of time that passes? Well, you know that a snowball, gets bigger as it goes on because it's accumulating more snow. So we know that del S dt, this change in size as time goes on, picks up more snow as it's bigger. So it gets bigger, and it gets bigger and bigger, kind of like compounding interest or something like that. They usually use this analogy. So it's accumulating more snow. So we can say that, the change in size is proportional to, let's say, the size of it at that point, just because, at this point it's picking up a lot, so it's, gaining a lot of more snow, but at this point, at the very beginning, it's pretty small, so it doesn't make a lot of contact with other snow. So let's say del S, del T, let's say, I'm not sure if it should be equal to, but let's keep it as is equal to its mass, or it's equivalent to its mass at that time. So I'll just write mass. But we know that mass is also changing as time goes on, just because you can see it's getting bigger. Its mass is also changing. And that's what we want. So that's good. So it's somehow proportional to a mass at a certain mass at a certain time. Let's say t, or tau. So we need to pick a mass then at a certain time, because remember, we're trying to find how big will it be at the bottom. So we know that it's about 10,000 feet. And let's just say, it takes it 45 minutes to go down. That's just your estimate. So del M del, where did I do S? Why did size? Del S del T equals, or is equivalent to M. I'll do that. So you need to pick this mass, so you could either, pick this mass, but then you'd say, oh, that's pretty small, it's underestimating. Or you could pick this mass at the end, that would probably overestimate it, because, that's a big size, and at the beginning it's not that big, and that would be accounting for too much. Or if you're a little bit smarter, I guess, you could do, some people would say, you could, go to the middle snowball and take the average of the two and use that to calculate your difference. But what calculus does is it allows you to, instead of assuming that there's this final stage and there's this beginning stage and this end stage, and then you just take the difference of those two, which is like this, del S, and then this would be del T. You take the slope of this, del S, del T, then you divide, that would be is equal to the slope of line. However, we actually know that, if you take the average, for example, it would go more like that. So as your number of spaces increases, it begins to be more curved. So obviously you want a nice looking line when you're ever thinking of something in algebra that you draw. You want to draw something like this, and that looks nice. People like curvy graphs, as opposed to doing like this if you want to do everything. So that's what calculus does. It allows you to solve for everything in between. So instead of having a graph that only looks like this, and this would be like, your change in area right here. Because that's how much, that's can be used in this area. That'd be overestimating the size of the snowball. But you find that it's proportional to ln of t, so it's something like might be e to the t. Yeah, it's e to the t. That's very good. It starts at 1, goes 2, and that's where e pops into. How do I stop recording?